In this talk, we're going to listen about elements of scalable architecture and some examples, if I read correctly in the description, by Goran Peretin.
All right, thank you very much. Hello, webcam. I'm very happy to be here, and thanks all for coming to my talk. Last time I gave a talk at webcamp, it was that room right there. It was 4 years ago, and I had a live demo where I played cartoons on my slides. I think it's going to be hard to top that, but I'm going to try. My name is Goran. This is my Twitter handle. You can find me on Twitter. I don't tweet a lot. It's just jokes, and they're all funny. I try a lot. I'm originally from Zagreb, about 10 kilometers that way, I think. I currently live in San Francisco, and I work at Twitter. More specifically, I work at the tweet service team, and internally, that team is also called TweetyPie. I'm sure you recognize this guy right here. And a fun fact, for reasons that are not known to me, this is not the team logo, though I really do feel bad about that. What tweet service team is, or what my team does, is we take care of all the backend stuff for anything tweets related. So if you're trying to tweet, or if you're trying to view tweets and it's not working, it's highly likely we mess something up. Obviously, it's a networking issue. What is this talk about? In the talk summary, I mentioned that this is going to be a technical and non-technical overview of elements you should consider when working with systems on a large scale or complex systems. And we're going to look at this through two components. The first one we're going to look at is something I call capacity scaling. And this is what we software engineers usually mean when we say scaling. This is purely technical concept in a sense that how many requests per second can your system handle? How many requests can this endpoint handle? What does this data store do? How much data can you shovel in it? So it's a purely technical concept. We talk a lot about this because this is very easy to talk about. It's easy to measure. So it's easy to explain as well. However, there is another concept that I really like to talk about when it comes to scaling and evolving large-scale and complex systems, which is habitability. So have you ever wondered why is it easy to add features to some systems and why is it hard to add features to other systems? Why is it easy to onboard new engineers to some projects and hard for another projects? Why is it easy to get rid of bugs in some projects? So all of that comes into habitability, and the premise of this talk is that it's not enough to make a system that scales highly in terms of capacity. If you have the most scalable system ever, if you can't add a feature to it or if it's really hard, it's really not all that useful. And an interesting point to note here is that the term on the left, capacity, is a purely technical concept. So if you have a system that can handle 20,000 requests per second, and tomorrow you replace the entire team that's working on that system, you still have the same exact system that can handle the exact same workload. Habitability is not. Habitability is also tied to, say, the composition of the team or your environment or the company you work at. This is what makes it hard to understand, reason about, and this is why it's oftentimes neglected. However, it's still quite an important concept. This is not going to be a deep dive talk into technical details of how we do things at Twitter. There's a couple of reasons for that. I only have 40 minutes, and I can only say so much in 40 minutes. The second thing is what we do at Twitter is highly specific for Twitter, and it might not be useful in your environment. And now really what I really want to do here is leave you with some questions you can take to your own company, your own environment, and then see how can you use some of these things over there. When it comes to questions, I plan to have a couple of minutes at the end for questions. However, if there's no time for your questions or you have a question regarding to some technical details or something that I skipped, please, I encourage you to catch me in the hallway. I'm going to be here today and tomorrow, and I'm happy to talk about anything software related. One more thing that I mentioned in the summary of the talk is that we're going to be talking about large-scale systems. I'm sorry. This is the largest scale you can find on the internet, verified by an extensive search. So to give you an idea what I mean when I say large scale, the systems I'm going to mention today are running on thousands of instances. We're talking millions or tens of millions of requests per second, huge caches, terabytes of caches, petabytes of data. So that's kind of the range of things I'm talking about today. Cool, so let's talk about capacity scaling first. So when it comes to capacity scaling, there is really not much new things I can say here. It's all been said on the internet. If you need to have a system that scales highly and it's web scale, you need to use MongoDB. So we can just go, oh, this is a joke, I'm sorry. Somebody said Jesus in the first row. Cool, so, all right, so on a more serious note, we're gonna look at these 4 aspects of capacity scaling. So what are we optimizing for? It's quite rarely that we need to optimize for all the use cases ever. We're gonna look at some constraints and data we have to work with, and then finally, which parts actually need to scale. This is my Twitter home timeline. So this is what I see when I open twitter.com. The thing on the right is what we call a home timeline. To render the home timeline, what needs to happen is we need to fetch all the 93 people that I follow. We need to fetch all of their likes, tweets, retweets, and all the other stuff. We need to combine all of that into a unified timeline. We need to order it chronologically. We need to do some processing on it. Then we discard vast majority of that and return just the top 20 items. So that is a lot of work. Additionally to that, besides being just wasteful, it's also unbound. What I mean when I say unbound on the server side is that we can't actually estimate how long this is going to last. Some people follow tens of thousands of people, and if those people that they follow tweet a lot, this can be a lot of work to be done on the server side every time we need to show a home timeline, which is literally every time you open Twitter. So additional to that, we figured out early on that we are much more read-heavy than write-heavy at Twitter. People consume tweets a lot more than people write tweets or post tweets or delete tweets. Every time you open Twitter, that made a lot of requests on the server side to get tweets. So in terms of the numbers, we do, I mentioned before, tens of millions requests per second on the read side, and writes are measured in thousands or tens of thousands. So what is the problem here? We can't really do all of this work every time somebody opens twitter.com. We have to have another way. We have to have this prepared somewhere on the server side, preferably in some cache somewhere, so every time you open twitter.com, you have this timeline rendered quickly. And this is what we do, and it's called fan out. So every time I tweet, you saw maybe previously up here that I have 325 followers. I was kind of hoping that's going to be 400 by the end of this talk, but no pressure. So basically what happens every time I tweet, there is a tweet service. This is a service my team owns. It gets a post-tweet request. And among other things, we also call a specific service called fan-out service. As the name suggests, that service does fan-out. So we store some metadata about the tweet that I just posted into 320 timelines. So for all of the people that follow me, they get that tweet right there. Why do we do that? So when they log on, we can just read their timeline from cache. We do not actually collect all the people you followed and all of their tweets, because that would take time. So we are basically trading off some cache and some storage space to make it faster in terms of render time. And then the bottom side of this picture shows what happens when you open twitter.com. That hits a timeline service, which renders the timeline, and they can just read the timeline from cache. So this is basically an example of the optimization. So what you can do in your systems, I think it's really important to figure out what is it that you're actually optimizing for. Do you have, if you're working on a web shop and there's a product details page, that should render really fast. But for those 0.5% of people that actually buy something, it's totally fine if the checkout is like 5 seconds or something, like when you push the buy button. So consider what are the trade-offs, what are you actually optimizing for? Next up, even though I don't have a lot of followers, there are some users that have a lot of followers. Katy Perry has over 100 million followers. Imagine what happens when she tweets. A lot of things get stored on a lot of places, right? So earlier when I said we do fan-outs, we do indeed. And the problem is if we do 105 million writes to a certain cache instance or cache instances, there's a lot of them. Katy Perry is going to wait for quite significant time for her tweet to be posted. So what we do is we do that asynchronously. And this is an example of a constraint. So what is the constraint in your system? For us, the constraint is we need to be able to read something fast. We also don't want users that have a lot of followers to wait quite a long time. So the path that I mentioned earlier, where we call fan-out service, that's actually happening asynchronously. We don't make our users wait for that. And we are OK with that. We're totally fine. It's really hard to come up with a system that can do 105 million writes instantaneously. It would be awesome if there was such a, let's say, SQL database. You could just do it one transaction. That's kind of hard to come up with. So another constraint that we do have, however, is that we do not drop a tweet ever. If you tweet and we say it went OK, we cannot lose it. So the one thing that we do synchronously is store it to our persistent data store, which is called Manhattan. I'm not going to go into details on Manhattan here. Just to give you a comparison, it's similar to Amazon's DynamoDB, and I have a link in my resource page where you can see details on how this is implemented actually. So these are the constraints, basically. These are the questions you can ask yourself to use in your system. So what can you delay for later processing? And if you can do something asynchronously, that's a huge advantage. You can put it in some queue, preferably persistent queue. You can retry it. If it fails, it doesn't impact anything else. If your worker fails, some other worker picks it up. It's really, you're much more flexible if you can do that. So this is more of a business decision than a technical decision as well. This is something you have to discuss with your product people in terms of, is it actually OK if some users get the tweet from Katy Perry a couple of seconds after the other users? So that's something to consider. The third thing is data. So is your data inherently, does it conform to the same schema? Is it all random? What are the access patterns? And I think this is something that dictates the decisions you make when it comes to using the data stores. You shouldn't use, I don't know, some data store just because it says on their webpage they can support huge write load. Does that data store support the write and read access patterns that you have? Do you read a lot more? Do you write a lot more? So in terms of mutability and cache, these are tightly related. I'm going to tell you what we do at Twitter. We use memcache. You saw Redis earlier on the slides in terms of timelines cache. Timelines are actually use Redis for cache. Tweets are actually stored in memcached. To be specific, it's not memcached. It's our internal version of memcache called twemcache. That stands for Twitter memcache. It is open source. You can find it on this GitHub link. In terms of numbers, our cache rate is around 94%. That is average hit rate. At any given point in time, there is over 50 billion tweets in cache. This is for each data center. And then some other details. We do over 30 million requests per second to our cache in each data center. So what we cache is some obvious stuff that everybody sees, like tweet data. That's immutable, so it's nice to, it lends itself nicely to caching. We cache counts, which is quite interesting because counts are highly mutable. Counts change a lot. However, we also need to return counts. Most of the times we return tweets, which means tens of millions of times per second. So there's really not much other place you can put counts if they change quite a lot, and you have to return them with all the tweets. We also store some immutable data from other services, which is quite interesting. And this is a pure example of a trade-off I mentioned. We are trading off latency on the read path, where we call some other service, for some cache space. So we are OK using more cache space so we can reduce this latency and don't have to call this other service all the time. We also call some mutable data, though that introduces all kinds of troubles with invalidation policies. So that is something definitely to consider. Just to tell you how much we rely on our cache, we had an incident a couple of months ago where our persistent data store, Manhattan, was unavailable for a brief period of time. And we were able to serve over 80% of all the tweet reads. And so all of those tweets came from cache. And the reason it's not 94% that I mentioned before is that we do some additional processing depending on the request, which parameters of the tweet you actually requested. So that was quite interesting. So persistent store was not available. Still, we had a pretty good success rate considering the circumstances. And then finally, when it comes to capacity scaling, which part needs to scale? I mentioned an example before of a web shop, if you're working on a web shop. Again, product listing pages, product searches, filtering, and all that should probably scale to a higher extent than the checkout service or something, however you do checkout, right? So It's not uncommon to see some services being extracted into separate services at Twitter just because they have different scaling patterns. If you extract a service into something else, you can also consider using different data stores. Maybe use a relational data store that provides some nice guarantees you can use, so you don't have to implement, say, transactions in application logic or something. In general, what I want to say with this is that oftentimes you would highly optimize a certain code path, and then that you made some compromises in terms of readability of the code. Be careful when you do that. Try to identify the hot paths in your system and optimize for those. At the end, when it comes to capacity scaling, you might notice that it's just a huge trade-off. You're trading cache for latency, or cache or synchronous versus asynchronous. What can fail, what cannot fail for you to successfully return a request. I don't like to call it trade-offs, I like to call it compromises. It's a conscious decision that you make, that you are doing it this way because this is what's important for you. So on a truly large scale, you're going to have to make some compromises. You're going to make decisions based on the environment and the assumptions you make. Okay, so environment being your current team, your current product direction, the requests from product managers, and the assumptions are, we assume we're not going to have a double growth next month or something like that. So these environment and the assumptions are called context, and how you deal with that context has a huge impact on the habitability of your software. Before we dive deeper into this, let's actually see what habitability is. This is a paper, or perhaps a book. It's a 260-page paper, so maybe it's a book. From Richard Gabriel, and it says that habitability is a characteristic of a source code to be changed confidently and what does it say here? Comfortably, okay? So this was written over 20 years ago when large scale and complex systems were not as widespread as they are today. So I would like to extend this definition, not to say that it's just the characteristics of the source code. It's a characteristic of the ecosystem. There are some things outside of the source code that can increase the habitability of your code. If you have pretty good documentation, for instance, it's going to make it easier to evolve the system and change and be confident that you didn't break something. However, the source code part is absolutely huge. If your code is a mess, obviously that is the component that makes it the hardest thing to change. Let's take a look at this brief video here. I'm not sure if this is going to work.
Here's this problem. Okay, well, how do we keep ourselves from programming ourselves into holes? What does that mean? It means that we make decisions early in some process that spread all over our system, the consequences of those decisions, such that the things that we want to change later are very difficult to change because we have to change a very large amount of stuff. That's the problem. Okay? And I want to figure out ways that we can organize systems so that the consequences of the decisions we make are not expensive to change. We can't avoid making decisions. Okay? But we can try to figure out ways to minimize the cost of changing decisions we've made.
So this was Gerald Sussman. He's an MIT professor, and this is from the talk called "We Really Don't Know How to Compute." It's on YouTube. I also linked it in the resources section. He's also known as one of the co-authors of the book Structure and Interpretation of Computer Programs, which is a seminal work, especially in the functional programming community. And this is really spot on. So we can't avoid making decisions. We can't avoid changing software. That's where software is. We change it. We add new features. We remove bugs. What we need to do is, and what we need to focus on is, how do we make some decisions now that are not going to make it harder for us to change the software later? So what can we actually do? How do we write software that's easy to change? That is the biggest problem here. That is what habitability means, and that is what makes your systems evolvable. So how do we write software that's easy to change? Obviously, this thing is stopped working. I didn't want to say obviously this thing stopped working. Obviously, we use design patterns. That's a joke as well. Cool. So no, but there's an interesting story on how this book came to exist. These guys, there's 4 of them. They wrote the book about 20 years ago or more. And what they did is they took a book called Pattern Languages from a guy named Christopher Alexander, who's an architect, like architects buildings and stuff. And he wrote this book called Pattern Languages where he described some patterns on how to do architecture. So they thought, why don't we just apply that to software? So they did that. It wasn't a big success. I'm not sure how many of you use these on a daily basis. I must say I really don't. The problem, why did it not work? And this is not the only effort to try and take some lessons from other industries and apply them in software engineering. The reason this did not work is that software changes. So architecture and buildings do not change. Once they are built, once you build a 30-story skyscraper, nobody is going to walk in and say, can you make it 40-story? So, yeah. Or if you build a residential building, nobody's going to say, can you make it a stadium? And this is the inherent property of software. Software is changeable. We have to change software. So what is exactly the problem? Just another note on design patterns. They did succeed in one thing, though, and they succeeded in sharing the context. And we're going to see what context is in terms of software engineering a bit in a couple of minutes. However, if you read this book, and I read this book, and if we were talking about a certain piece of software, you didn't have to say, you know, there's a class and it has a list of these other classes, and when a method is called, it calls all these other methods. You could have just said, oh, that's an observer pattern. And I would know what you are talking about. So we had some shared context, and you could have just used the reference and the name of something, of a certain structure in software, and I would know what that is. So I think that book did do some good in that area. So let's take a look at what exactly makes software hard to change. Why would some piece of code be hard to change? This is a snippet of Python. To all the Python folks in the room, I truly apologize for the 2-space indentation. I don't know what happened there. I hope you don't mind. I haven't done Python for a while. So this is a function. It really doesn't matter what it does. It has a really stupid name. This is a bad name for a function. So to change this function, you got to know 2 things. You got to know what the function is doing, and you got to know why is it doing that, what it's doing. And keep in mind that why part in most of the software systems and most of the pieces of code is quite obvious. If you're using Django or Rails and in your model you have a method that's called save, it's quite obvious why is that there. It saves something to a database, right? So how do you figure out what is this doing? Well, you can read it, right? You can read every single line of the function and you're going to know what it's doing. That's cool. That's kind of easy, right? There's a better way to write these functions, which is this one here. Somebody added a comment that says it sorts numbers. The function indeed does sort some numbers or some elements. And there's an even better way to write it, which is you just give it a proper name. However, none of these things tell us why is that here. So the problem in this instance is that Python, as many other languages, has a built-in sorting function, which is written by people much smarter than me. And it's heavily optimized, and it also works on numbers, of all things. So why would somebody put this in their source code? Why is that there? And this why thing is what's preventing me from changing it, because I might break something. There's really no point in that being there. And that's a really big thingy. And if this was a bit of a contrived example, and you wouldn't really find a lot of these custom sortings in the source code. Here's a couple of higher level examples that we can take a look at. Why do we cache some things and don't cache other things? Why does a user table in a database have the number of products that user bought? Why is the primary key that we chose, or why do we call some endpoints, mark them as just being internal only? So these are all the things that are not immediately obvious. So anything that's not immediately obvious, we have to know why in order to confidently change it. So basically, I already said it. Why is a problem? What is not that much of a problem? Because usually you can find out what something is doing. If it's on a code level, you can just read the code. If it's on a wider, higher system level, you can perhaps read a system design document, if there is such a document. You can trace the calls between services. You can see what is going on. At the end, it might take you some time, but you can see what is going on, because what is an artifact of the code. So what is a consequence? If you have the code, you can figure out what is going on. Why is actually not. Considering all of that, I believe that getting better at sharing context or have less context to share is a single thing that can hugely impact your habitability of the software and how quickly and effectively can you change software. And one more reminder again, keep in mind we're talking about large scale and complex systems here. If you're working on your home project or a hobby project, much of this might seem as an over-engineering. So apply some moderation as to when to use stuff like this. Cool. And when I say sharing context, I basically mean share context around the why. I'm not saying you should never share context around the what. If there is a really confusing piece of code and sometimes you have to do that, or a convoluted piece of code, or you have to implement something that really doesn't look nice in your language, it's cool to provide some documentation as what's happening. So let's take the have less context to share first, and then we're going to see how to get better at sharing. There's a couple of things you can do. The first one is use known and obvious technologies. Have you ever wondered why some companies hire Rails developers or Django developers, and other companies are just hiring general software engineers, and they're saying, well, a good developer is a good developer in any language or a platform. Are these former companies, don't think that? Like, what's going on there? And it's mostly because of the context. If they hire a Rails developer, they assume that that person has done some Rails work. And Rails is an example of a technology that assumes a lot of context. If you and I walk up to a Rails application that we've never seen before, we know a lot about it. We know the flow through the application. It's through the controllers and models and then back through the views. We know where things are. If we need to add a column to the database, we know where to look. We know where the custom code is. I hope that's a resolved discussion in the Rails world, by the way. So Rails and frameworks like Rails and Django, and there's a bunch of other libraries, they assume a lot of context. So make it obvious. This is an example where a lot of the source code is actually quite obvious. I mentioned a save method on a model in a Rails or Django application. That's quite obvious why it is there. Another way to make it obvious is to use some sort of self-descriptive technologies. For example, Thrift versus HTTP, JSON HTTP APIs. This is not to say you should use Thrift always, but Thrift is an example of a technology that is self-explanatory, it's obvious. If you see a signature of a Thrift RPC call, you exactly know what's the method called, what exactly is going in, what is the type of things that go in, what comes out, what are the types of things that come out, and what are the exceptions that get thrown. HTTP, especially if you use JSON, tells you none of that. You have to write the docs separately, maybe use JSON schema that shows some types, but basically it's just a hassle. So, for instance, Thrift is an example of how things can be very obvious. And then avoiding overuse of an abstraction. This is also a slippery slope. Of course, you need to use abstractions. We develop software. It's all abstractions at the end of the day. Every time you use an abstraction, you're assuming a lot of things. You're assuming that people are familiar with some internal details of what you're abstracting over. And that internal thing is called model. So people need to know some things about what you're abstracting for. And then you're also assuming that people have the same use case as you have. So basically, their use case is going to fit into your abstraction. It's easy to overuse the abstractions. So at the end of the day, especially in large-scale systems, there's only so much you can do to have less context. As your system becomes larger and has to scale more, you have to do more and more custom things. So how do we get better at sharing context? Well, one thing, I want to get this out of the way first, because people usually don't like it. It's obviously to write documentation. Good documentation doesn't document what is going on. Again, that should be visible from the artifacts, like source code. A good documentation describes why is something happening if it's not clear. Try to document the environment you were in and the assumptions that you made at the time you made this software, because this is what the person down the line, a year down the line, your colleague or maybe even you, this is what that person doesn't know. They see what you have done. They don't know the environment you were in and the assumptions. They need that in order to effectively change the software. Recording a screencast, I've just recently discovered it takes literally 3 clicks in macOS to start screen capture. I'm sure there's a software for Windows. If you're on Linux, I'm really sorry, just give up on this. Code surfing sessions, these have become quite useful. We do this in Twitter a lot. Good code surfing session is not somebody reading the code and then 10 people in the room listening. A good code surfing session is more like the person that's doing the code surfing session is kind of recreating the components you are analyzing. And while it's recreating that, it's mentioning what are the problems and obstacles in the actual code. Unfortunately, this takes significant time on behalf of the person preparing it. Code reviews, at Twitter we have mandatory code reviews, meaning nothing gets merged to master if it's not being code reviewed. And this is really not sort of like a veto process in a sense that you're going to say that my code is not good. This is great for sharing context. If I send out a code review, the rest of my teammates know what's happening. The on-call person knows, oh, this got merged in today, so if I get paged tonight, this might actually be the reason, because this changed recently. And as with many things in life, this gets a lot easier if you establish this as a habit. If you have a goal, goals are awesome. If you set a goal to document a certain sketchy part of your application, that is great. You're going to sit, you're going to document it, and there's documentation for that part of the system. However, if you establish this as a habit, for instance, if documenting weird and unexpected things in your system is a habit that you do as you're developing the code, it gets much easier. So for us, code reviews are a habit now. I don't see it as a hassle at all. In fact, I look forward to it. I get to learn a lot of stuff this way. Peer programming, this is a sketchy one. It works for some people, doesn't work for other people. In peer programming, I found it, it's much more useful to me for learning opportunities than the output. So when I pair program with some folks, we don't always, almost never actually, implement the feature fully that we planned. It's more in terms of the sharing the knowledge and tools that somebody else uses, and that can improve my workflow. And then when it comes to sharing context, pro tip here, optimize for creating. If you have to click 4 clicks through a really slow wiki page and then write in some media wiki format that you don't like, to write some documentation, you're just not going to do it. That's just not going to happen. Optimize for writing. I like to write my stuff in Markdown, and I like it to have in my editor because it's always open and it's quick access. So what I did is I just write it there, and then use the tools to optimize it for reading. So use the tools to transform that from whichever format you write in to whichever format your team uses to share documentation or stuff like that. Tools today are quite powerful. Don't get something like cumbersome system you use get in the way of you sharing the context. Cool. So this is a scientific graph that shows which context should you share. Up here on the y-axis, we have the level of things. So up here is the system level, kind of the entire architecture of the system. Down here is the lowest level, which is like code or a function. On the x-axis, we have what is going on, and then we have why is going on. So in terms of high-level abstract stuff, maybe system design, you should almost always document why is something the way it is. You're also going to find out, as you do that, you're also going to find out that high-level stuff tends to change a lot less, which means you have to update the docs a lot less, which is always nice. So you don't change the architecture of your system every week. However, code does change every week, right? And then, as mentioned, for code, usually you don't have to document what it's doing. There are some occasions where, if it's really unexpected what's happening, you should provide some docs as to what's going on. So I know what you're thinking right now. This guy is basically telling me I need to write docs. And then, that's a bit of a problem. This one is first. So nobody likes to write docs. You have to maintain the docs. And then, what is actually the incentive for you to do that? What is the incentive? Why would you do that? So the incentive, the reasons are obvious for your teammates and the people that join your team later, or your company, your organization. It's obvious for them. It's all nicely. The context is shared. They can watch a couple of screencasts, read some docs, do some pair programming, and they're up to speed, they're up to date, they're productive. What is the incentive for you? So this thingy, okay, it's working. So it's easier to pick up the work and understand the work later on. And this doesn't mean just for other people. This also means that you can do it. I'm not sure how's your memory, but here's an example. In my free time, I work on a trading system. I wrote a program that trades futures for me. It's sort of similar to stocks, but it's futures. And so I developed some of that stuff, and then this is a code snippet from there. Obviously, I'm not a noob. I'm not just going to use a number in the code. So I extracted it into a variable. I gave it a nice name. I think this is a pretty nice name. It's a multiplier for forecast diversification, right? And then a couple of months later, this is what that code looks like right now. I actually don't know why is this 1.31. I know what it is. I can see where it's used. I multiplied the forecast by it. I just don't know how did I come up with 1.31. And then, this can happen. Some jerk put it in. Interesting thing is if you look at the code history for this project, it's all the same guy. So again, it's not just for other people. It's also going to be easier for you to walk in later and use the software. The next thing is onboarding other engineers. I kind of mentioned this one before, but this also means more free time for you. It means that new people or people that just join your company or join your project are not going to bug you with a lot of questions. And I'm not saying you shouldn't talk to your teammates. You really should. You can perhaps talk to them over a beer or some chilapi or something. However, it's also less frustration for them because they don't have to rely on you. They can just be self-reliant. They can ramp up faster, they can be productive and more effective quickly. And onboarding is important. We change jobs more than ever. So while it was typical for your parents or maybe grandparents to work in a single company or a factory for their entire work span for like 35 years or so, this is the average tenure for tech companies in Silicon Valley. I couldn't find the data for European companies and Croatian companies, unfortunately. However, these are all the cool companies. This is where these have like catered meals and food and everything, and it's also, well, there are some exceptions. And everything is great, and people would want to work there, but the average tenure is 2 years. So we're going to change jobs a lot, and there's going to be a lot of people joining your team. This has huge payoffs. So final two things is that it can also help in learning and retrospective. If you have the context shared from before, you can try comparing what did you think before and what do you think about it 6 months after. You're going to start seeing some patterns. You constantly make the same mistakes. You're going to identify some things that you can proactively improve for future. And finally, this one is great for me. Oftentimes, it's like trying to see if you know something. How do you know if you know something? Well, if you try to explain it to somebody who has no idea about it, then you can say you know something. It's the same with this. If you can, oftentimes I try to write something down, what I'm thinking and what I want to do, and then I see it makes no sense at all as soon as you start writing it down. So in conclusion, I truly believe that the way to develop and evolve large-scale software systems is to ask the right questions and share the right context. The reason is, if you do that, that's going to enable you to change and evolve your software, and really, that's what developing software is all about. Thank you very much.
Okay,
I think we have
do
time
we
for
have
some...
any questions?
Yeah.
Oh.
Hey, I have a quick question. So you mentioned thrift. So does that mean that all your services communicate over like a binary protocol, or do you use any textual protocol? Just wondering if that impacts performance at all in terms of scaling, the deserialization of messages going around?
That's a great question. Yes, internally in Twitter, we do use thrift. We use custom protocol called MUX. It's also open source. This is all encapsulated for us by our service framework called Finagle. It's also open source. And in terms of the performance, we actually see better performance by using that than HTML or JSON. So we do use binary protocols, and it is faster for us.
Okay, any other questions?
Hi. Question on the docs. You explained well, yeah, there's use from the docs. However, the problem with the docs is when, even if you have good intentions, it can happen that they go out of sync from code. And that can be even more damaging than no docs, because you're looking for Y, and you find the wrong Y, and now you go back and you modify it based on wrong assumptions. So is there anything special that you do at Twitter to minimize those instances or somehow eliminate?
Again, a good question. So what I found works for me is that really trying to establish it as a habit, and then I push it onto my team. Of course, if your team is receptive to that. So for instance, what I would say, if you're developing some features and you did something, I would, on the code review, I would ask you, hey, can you actually update the docs on that over there? Obviously, that works for proactive, for the things that are going to come up. If the docs are already written and they're out of date, I really don't have a good tip for that. Yeah, that's a problem. Yeah.
Okay.
Any other questions? Okay, I have one question. So for habitability, if, let's say I'm going back to work on Monday and I want to do, I want to start something to improve habitability. So from all the things that you mentioned, which one would you recommend like the best trade-off? Which gives the best trade-off? Which should I start first?
As the new people, grab the newest person on your team, ask them what is the hardest part for you? What do you not understand? What do you think would help you onboard faster? What do you think would help you be more productive? New people are awesome. Because when you're working on something, you have all this tribal knowledge in your head, and some things, a lot of things actually are quite obvious to you. Obviously, we call that service to get that data. New people don't know that. I think that's a huge one, as the new people.
Okay, another question.
Hi, back to architecture. So are you saying that you're computing the timeline even for people who are not really using the Twitter at the moment?
Yeah, that's a great question. Not really. So if you are not using Twitter right now, and I tweet something and you're following me, yeah, we're going to insert it into your timeline. However, if you haven't opened your Twitter for quite a while, that's going to go out of cache. So in that case, no, we're not going to, obviously there's a persistence store for timelines as well.
Obviously, you've studied the trade-offs between computing the timeline from some kind of a in-memory database and having it pre-computed. So I'm wondering, are you still researching on different solutions around it? Because it seems quite expensive to do it, even for people who are, I don't know what's your cutoff point of activity, but yeah, just some comments on that.
So if you haven't used Twitter for a while, if you haven't opened twitter.com or use your mobile app, we don't actually cache your timeline. So I am not sure what the exact cutoff is and how it gets evicted from cache, because that is the timelines team. But I know it's not in the cache in that case. So, yeah.
Any other questions? Okay, then that's it. Thank you very much.
Cool. Thank you.